What I'm going to talk about today is it's entitled Quantitative High-Speed Scalar Imaging in Turbulent Reacting Flows. And in case I forget at the end, again, I don't work alone. I have many postdocs and students that work very hard on this. So before I give you an overview, I'll put your attention into the lower right-hand corner of where we see high-speed imaging circa 1887. Okay, so this is Edvard Muybridge. And so what happens in the late 19th century, for those who were interested in animal locomotion and also they were also interested in restarting their computer, is that whether or not a horse's feet were actually fully off the ground during trot or gallop. Now, you may not think this is an important question, but it was in the 19th century. Basically, artists always had painted the feet going straight outwards, and many thought that a foot always touched the ground. So here's a case where Leland Stanford paid a lot of money to set up a series of linear photographs that would be tripped by, essentially thread by the horse, and you would take a series of snapshots as it moved down the field, and you get one of the first high-speed imaging examples. Now, this has nothing to do with lasers, it has nothing to do with combustion, but this was a targeted example of high-speed imaging that actually answered a question. Okay? And so again, that's what I hope is our motivation, is that we can use these tools actually to answer questions and not just take images. Okay? And so what I'm going to do today is talk a little bit about the challenges and opportunities we have, a little bit on high-speed imaging, and then what we do on the pulse burst laser, some examples through quantitative Rayleigh and Raman scattering, and then hopefully at the end, if everybody's not too hungry, do a little bit on resolution requirements, something that's, I don't think, talked about enough with the experimentalists, of exactly what you need to resolve and when you need to resolve it, and some concluding thoughts. And then if there's time and we still have this discussion topic, again, what is the best way to use high-speed imaging? So again, instead of giving a typical turbulent graph where you have this large range of length and time scales, I thought it would be more interesting to say, here is our challenge. If we start with 1 atmosphere and we look at a laboratory scale flame, we have some thickness of the reaction zone, whatever you want to define. Well, it has some thickness delta, and we have another physical construct that we're used to, a human hair. Okay? Now, as we go to higher and higher pressure, which is one of the focus of this workshop, this is going to get even thinner. It's going to become even more difficult. So we know that things are small. But we also know that things are large because we have device scales. So this already, our brain's already thinking we have a large dynamic range. We also move fast. This is just visual luminosity from a diesel engine. So we're not resolving any dynamics here. We're not resolving any turbulent flow scales or anything, but we have a couple of these processes in the time that it takes to blink an eye. So we also have these very fast processes as well. So this is one of the main challenges in turbulent combustion measurements, is that we're looking at small things, fast things, and then they also spread up into much larger. So we have this constant idea of a large dynamic range, and we have some very stringent requirements. So the selling point, the tagline for laser measurements, is always that they're non-intrusive, they give you pretty good spatial resolution, i.e. at an atmosphere, you can get the probe volume pretty small, and you can freeze the flow. Okay, so that's for 30 years what's been sold. And then over the last decade, where high-speed imaging has come online, we now say, okay, now we have the opportunity to investigate dynamics, transients, and temporal evolution of temporal topology of the flame. And these are outstanding motivations. And the reason why you want to do imaging is you want to keep the physical structure that came from instantaneous imaging, okay, that's been developed over the last 20, 25 years. And then you want to go back and still take advantage of the temporal history that existed in probe measurements decades before, and therefore you want to start trying to take advantage of some of these high-speed imaging, these high-speed measurements. Okay, so before I talk about the pulse bursts, again, the most common approach still is to use commercial available systems. These are wonderful systems. They give you continuous operation. Measurements have been reported from 5 to 50 kilohertz. I wouldn't call them plug and play. I don't think anyone that uses them would call them plug and play, but they are readily available. You buy them, you can get them set up, and after only sending them back a few times to the manufacturer, you can take some data. And so one of the things that we want to think about is that they have limited pulse energies. Okay, so this is not a problem for many diagnostics, but for some of the diagnostics that are staple in combustion that I'll talk about today, whether it's Rayleigh or Raman scattering, spontaneous Raman, or the idea of some of these fluorescence diagnostics at high pressures, these limited energies may be a problem. So one thing I want to talk about are these two examples, though, just showing the real utility of the commercial systems. Here's work done at DLR and on the left, and work done at Michigan with Volker Seek's group at Michigan. The reason I always leave these two examples in my talks, even though they're getting a little old, is that this is an example where you took these high-speed imaging diagnostics and you applied them to extremely complicated systems, and you were using them for targeted purposes. So this is a model gas turbine, and it's the idea to look at the coupled velocity through PIV and OH to look at the interaction between the velocity field and the flame front and try to start understanding this precessing vortex. And again, in the engine, to look at the coupling between the fuel concentration via a marker in laser-induced fluorescence and the velocity field. And so this is an example where it's not just applied in a laboratory or some of the type of flames that I've looked at, but more of these really complicated environments. So they're quite nice. So an alternative way to make these measurements instead of commercial systems is use something that's been referred to a couple of times today as a pulse burst laser concept. And let me see if I can explain that. Let's say you start with a very low power continuous beam. You have either a pulse laser or you have this laser pointer, and I click it really fast over and over again. Okay, so I start with something very weak. And if I amplify a finite portion over a limited duration such that I give it substantial amplification, I can generate very intense, very high energy beams for a finite duration. Okay? And so again, start weak continuous beams, okay, and then you amplify a portion of these, and you end up with this burst, okay, of high energy pulses. You can end up with bursts that have energies as high as you get 10 hertz, the laser systems. I'll talk about that. But with the advantage now that you have spacing that's comparable, or most of the time exceeds that available with commercial high speed. We've demonstrated in my lab anywhere going from 10 kilohertz up to a megahertz. And again, some of the pros are high energies are available, high repetition rates are available. The traditional con, of course, is that you always had limited record length. These started out as being 400 microsecond bursts. They got to about 2 milliseconds. And then in my group, we've gone to 25 milliseconds. And then there's other systems that are even longer, although they have lower energy. Okay? So here's a laser system in my lab. This is a built NAR, so this isn't purchased from Spectral Energy. So this is a custom system. Because we want to achieve a little bit higher laser energy for some target applications. And so here's an idea where we start with a very low energy laser. This used to be a solid state vanadate laser. We've replaced it with a fiber laser. And then, but those details aren't important. Let's say we start with something microjoules, and we amplify it through a series of these amplifiers, okay? And all you care about is what comes out at the back end, okay? So we start with order microjoules, and we end up with something right now where the current output from the two combined legs is about 3 joules per pulse at 10 kilohertz. Okay, so we can do about 1.5 to 1.6 joules per pulse per leg in the fundamental. The burst duration is about 25 milliseconds, and so we've demonstrated 250 images at 10 kilohertz and about 100 kilohertz, 2,500 images. What we typically do is the fundamental is not readily usable for many combustion diagnostics, so we frequency double it to 532. And so here's an example of the system. Beam quality at the end after it's had about 10 to the 6 amplification, still pretty good. And here's a series of pulses over 20 milliseconds in about a year and a half ago almost, where we had about 70% of the system. Last month, we ended up getting greater than 1 joule per leg, one joule per pulse per leg at 532 at 10 kilohertz. And this was coming from 1.5 joules per pulse in the fundamental, so we had about 67% conversion efficiency to the green. Okay. So let's say we have a laser system, and let's say we can produce a lot of energy, and we want to do quantitative measurements. And because I'll talk a lot about that, is that the real challenges that come with making quantitative measurements. Well, we have another end too, it's the detector. Okay? So most of the recent high-speed measurements have used CMOS cameras. There's many brands, whether you're a fanatic of Vision Research, Photron, or PCO, they all have the same issues. Okay? And so this is something that Andreas has looked at and talked about and published work on, but there's not too many other comments on this. Lots of times we point and play. We take for granted that these things are CCDs. We point them at something, we get a measurement. Okay? And so what happens is these things can exhibit at times different characteristics than CCDs. Here's an example of non-uniformity. So it's an interesting non-uniformity too. Let's first talk about what a CMOS sensor is very quickly. This is what's referred to as an active pixel sensor. Every pixel has its own A to D converter, so think about it, you have a million little photodiodes looking at your flow. They all have a mind of their own, and they all read out information separately. Okay. So you can imagine, okay, there can be non-uniformity in terms of intensity space, but we've also shown that there's non-uniformity in terms of temporal response as well. If you look at one of our cameras and you expose it to light for 40 microseconds, which isn't that long, but we're calling it quote-unquote continuous source, you get a pretty good uniform. If you expose two different cameras to 20 nanoseconds, which is comparable for a laser-based measurement, you get quite a different temporal dependent uniform response. And we've shown this to be repeatable, and it changes as you change the duration. Okay, so this is one aspect. Nonlinearity, again, these need to be tested to see what the nonlinearity is. Some cameras are better than others. The one key point is that all cameras are different. Please test your cameras. Here's a case where we only saw nonlinear effects in the bottom 5%. Two things that I want to point out at the end that are extremely important. Noise for these cameras. Okay, these have a read noise of typically about 30 electrons. Okay, what does that mean? Well, all you need to know is that when you go and buy a really good CCD camera, things that like Rob Barlow uses at Sandia, the bad ones are about 6, the really good ones can be 1 to 2. So you can think about this as you have 15 times more read noise in the camera. Okay, why do we care about read noise? Well, we also have to couple this to the fact that CMOS cameras have a very finite dynamic range. These are 12-bit cameras. There used to be a fake 14-bit one by Vision Research that had 2 bits of noise. But these things are inherently limited 12 bits. They will not make anything beyond 12 bits. It's technologically not feasible right now. Okay, so you have 12 bits. So what does this mean? This means that that's 44,000 counts. Okay, for those of you who don't care about that, all you really need to know is that the read noise is the bottom 2 to 3 bits of your camera. Okay, and then if you start thinking about when I go through a flame and I have a simple experiment where signal is just number density, I have about a 3-bit change due to number density. So what does this really mean? This is that it's a challenge for experimental design, meaning that when we have high signals, we really need to put this at the upper end of our camera, okay? And then allow that the change in signal needs to not come too close to the noise floor. Otherwise, you're basically going to be measuring noise, or your signal is going to be compromised by noise. And I'm going to talk about that again in a second, is that looking at something like the signal to background of your camera is an increasingly useless quantity to look at. Okay? It gives you no information about your measurement. It needs to be the signal to noise, which is a precision value of your measurement, not what your gray level is. We don't care about that. Okay? So one of the bottom lines is that you need detailed calibration for these sources. So these are expensive. They cost $100,000. Please calibrate them. Okay? And then that's just the camera itself. You haven't coupled it to the high-speed intensifier, which again has higher noise. Charge depletion means that as you try to operate these things faster and faster and for a longer number of pulses, it can't recharge, and so you get lower and lower intensity levels. You get gradient blurring. You end up getting charge that spills to your camera, so you get incorrect gradients, or you can even get to the point to where you can't get you cannot get an appropriate representation of an intensity response function on a single pixel. Okay, and so the bottom line is that they need detailed calibration. Okay, which many people do, but it's something we need to take into account. Okay, so now once we do take the time to calibrate these things and go into measurements, the first example I want to talk about is planar Rayleigh scattering. So Rayleigh scattering is fairly simple theoretically. It's just the elastic scattering for small molecules, or again particles that are much smaller than the wavelength of light. It's proportional to a number density and a mixture average cross section. And what we have here on the left is an example from a non-reacting jet, so that we have the mixture fraction. We can measure the mixture fraction from the jet. And from the right, measurements within the DLR flame B, which is a methane hydrogen nitrogen flame where we can get temperature. A couple of things I want to point out. These measurements are taken at 10 kilohertz. Again, we work really hard in my lab on quality of measurements, and so what we have here is an example where we have signal-noise ratio, which is defined as the mean mean measurement divided by the RMS. So again, our signal to background is about 2,500, but it doesn't tell you anything, okay? So we have signal noise exceeding 200, which means that when we make a measurement, you would have about precision of about 0.5% there. And in the temperature measurements, we work hard to get to about 140 at 300 K and 55 at 2000 K. So we're trying to make the measurements as low noise as possible. Okay? So for those of you who don't like movies, here's an example 36 of the 200 stills, just so you can see sort of the temporal evolution of the process, and hopefully, even though we have about a 4-bit projector here, we can still see some of the fidelity of the imaging. Okay? And so again, just to highlight something, here's an interesting idea, the pros and cons about high-speed imaging, or something that Noel said of just doing one species. Okay? Here's an example where you can look at the dynamics of the temperature field. So you see just in a couple of frames, you can see going from high temperature to basically being what we could call ripped apart, going to low temperature and then rehealing. So the first thing you look at that and go, that's an outstanding example of local extinction and reignition. Well, it could also just be an outstanding example of flame coming back into the laser sheet. Okay? And so this is where you need to couple in other measurement techniques as well, whether they be velocity, and also some of the off-angle chemiluminescence that's been done at DLR is quite nice for looking at some of these out-of-plane effects. The one thing, though, we can see from this is regardless of what the mechanism is, it shows how quickly the temporal evolution of some of these even laboratory scale flames can be, and again starts to point you toward some of the potential utility of high-speed imaging. Whether or not that potential is realized or not is a different question, but it starts to show some of the potential of these measurements. Second example I'm just showing in terms of the technique right now is what we've done in developed high-speed Raman scattering. We essentially want to look at the multi-scalar behavior using time-resolved imaging. The idea behind spontaneous Raman scattering is that we then take our pulse burst laser beam, focus it to a 1D beam. The beam is then collected, both you get Rayleigh and spontaneous Raman that are then sent through an imaging spectrometer. The Rayleigh channel is sent to one high-speed camera, and the Raman signal is then dispersed via a holographic grating filter and sent to an intensified CMOS camera, such that you end up getting a two-dimensional array of your one-dimensional physical line image and dispersed in spectral space. And here are, from just two radial positions, examples from a hydrogen-nitrogen flame of just, we can see the major species of hydrogen, oxygen, nitrogen, water, and then again we actually see the vibrational, and this is rotational hydrogen. And so what we have here is, it's a little dim here, so I apologize. This is from DLR H3, one of the older TNF targets, Reynolds number 10,000. And what you see here are stacked up, so bear with me, the movies will finish before I do. These are your radial profiles, so this is 1D radial profiles stacked up in time. So this is essentially a spatiotemporal map of the scalars from temperature, hydrogen, oxygen, water, and mixture fraction. What you have in the lower right-hand corner actually was the temporal evolution in state space against mixture fraction. Okay, this is not a traditional scatter plot where you take a tremendous number of ensemble measurements. This is actually through one 15 millisecond burst. Okay, so what we have is 15 milliseconds of one-dimensional data. If we take one slice at 12 millimeter, you can get your classical single probe temporal profile. And then if we look at it in state space, this gives us an idea of how much the quantities are fluctuating around the mean. That's what the solid lines are as a function of time, just in 15 milliseconds. Okay? And so again, this gives us a different way to visualize and actually use the data in just a moment. Well, the talk was quantitative measurements. So we can always take a tremendous amount of data, take a couple hundred of these bursts, about 500 bursts per station. Again, we can always produce low order statistics. And so what happens here is the blue are the published TNF results from DLR. They're available on the website. And then the red are essentially our line imaging. Okay, so the ensemble, this is our mean and RMS. And we get pretty good agreement with the published low order statistics. So again, there's been a lot of work on calibrating the system, and especially with the high-speed intensifiers, to get quantitative results. We've only recently started processing hydrocarbon flames, so we've moved what you would call a difficulty from hydrogen to hydrocarbon is pretty intense, especially for a high-speed camera and a high-speed intensifier due to the overlap between a couple of the spectral features in the Raman spectra, especially CO and O2, N2, and all these. They have some overlapping problems. But here's a single burst preliminary from hydrocarbon flames and giving the scalars. And what this little tiny graph over here is just a quick scatter plot between methane, hydrogen, nitrogen, hydrogen, and CO2. The green is just the TNF scatter data, and the black is actually not a traditional scatter. That's just a scatter from one burst. It's showing that the measurements right now are not completely off basis. There's a lot more work that needs to go into CO. CO has a tremendous number of problems with the Raman channel, even in traditional 10 hertz Raman measurements, especially when you get to the high-speed system. This is by far the weakest measurement, and so we're still working on ways to improve that. But we have shown now that we can take now time-resolved 1D Raman measurements that take a significant amount of pulse energy and now move these to the time domain and end up starting to get temporal information on multiple species. So what can we do with that? One example is the simplest statistic is just to look at the autocorrelation in the derived integral timescale. And what the importance of this data is, this is at an axial position of 20, radial position centered at 1. This actually produces the autocorrelation for 6 different scalars. And the thing that stands out is that they're not described by a single time scale. They all have a characteristic time scale that changes also as a function of radial position, the relative time scales. And really, what you see here is up to about a factor 4 difference between the integral time scales here, with the fastest being the temperature and the slowest being the mixture fraction. As you move toward the radial, toward the stoichiometric contour, at least the average position, the stoichiometric contour, they start to become closer together, but they do never collapse. And what you see is on what would be the rich side of the flame, the mixture fraction usually follows the hydrogen. When you get to the stoichiometric contour, there's a flip, and the mixture fraction is highly correlated or follows, again, close time scales to the oxygen. And the other thing is that the time scales, autocorrelations in the derived integral time scales stay quite different until you get past the flame. So one thing you look at is you're looking for Sani checks. So we took measurements at x over d of 40 and beyond, where we're beyond the flame tip, and they do collapse. Because this is where you expect all the scalars to act as a passive scalar, okay? They're beyond the flame tip, they're not influenced by a reaction anymore, they're just hot, and therefore the time scales do ultimately collapse. So that's been one outcome of this work. One thing that we've tried to do is exploit the two-dimensional aspect is to now start looking at two-point space-time correlations. And so the whole idea, it's a little small, is instead of autocorrelation, we're going to look at the correlation between any origin point, call it here, R naught and X naught, and again, its displacement in space and in time. Okay? And so here's an example from DLR-A and DLR-B, an axial position of 20 diameters and a normalized radial position. And again, we end up generating these contours, and I'm going to talk about this, and what we end up getting in these, again, delta x, again, is the displacement moving from this origin down in the axial position, and again, in time, taking advantage of longer record lengths, 20, 25 milliseconds. And we end up generating these elliptical maps. And so what's the relevance of that? Well, your isocorrelation contours for Taylor's hypothesis should be parallel lines, okay? They're not. So what are the implications for this? Okay, so strictly speaking, we do know this, but Taylor's hypothesis is incorrect. That's fine. Well, let's see if there's some implication for that. Okay, we notice that these are elliptical. Well, the elliptic contours were suggested by Zhao and He in 2009. This is homogeneous, non-reacting homogeneous shear flows, wall-bounded flows, and essentially they took advantage of the fact that the correlations are to be elliptic to develop a so-called elliptic model. So what we wanted to do is see two things. One, does this elliptic model hold for reacting flows, not just passive scalars? Well, it was originally developed for velocity. Can we move into scalars, not just passive scalars, but active scalars in a reacting flow? And then also, can we use this elliptic model to understand the physics behind why this quantity is decorrelating? Because again, you can already start to understand that if these are elliptical, then the decorrelation is not just by convection alone. This quantity is not just convected downstream. There actually has to be other processes that lead to the decorrelation of the scalar. And so this is just of fundamental interest. So again, here's the simple Galilean transformation between time and space for frozen flow. This is Taylor's frozen flow hypothesis. And again, this is what was developed by Zhao and He, but it's a simple geometric representation of an elliptical contour. Let's imagine we define an ellipse, our minor axis, our major axis, and then we can look at the ratio. Well, then now our correlation can be broken down into, or our transformation, again, from space to time, we're looking at our correlation. It can be looked at in terms of two terms. We can change space and time, okay? If you look at what you're trying to do in frozen flow, you're trying to go from space and time to just space, right? And so the whole idea here is to still have a convective term. Now, instead of taking the mean axial velocity, we'll have a u parameter that's proportional to the way that which the quantity of interest is convected. And in this case, that's the scalar. And in we have a separate term, which essentially represents a random plus a shear term. And what that means is that if we take that basic fundamental tenet of turbulence theory is that the small scale quantities are decorrelated, okay? They can be decorrelated by either being convected by a point, if you think of an Eulerian framework, or they can be, if you have no mean velocity, think about homogeneous isotropic turbulence, they have to be decorrelated by turbulence somehow, so-called random term. But also when you have shear forces, the large eddies actually can distort small eddies as well, leading to an acceleration of the decorrelation process. So you have convection, and then you have essentially what I call the small scale processes here, okay? And then just from geometry, we can derive what these u and v parameters are just based on the elliptic contours. Okay, so here's some examples. So if we again take a look at 5 different positions, looking at 0, which of course is the temporal autocorrelation, and then we'll look at different displacements. Before we do anything, these are essentially the Eulerian space-time correlations you would expect, okay? As you go past a point, you increase to a maximum and then you decrease, okay? What happens in B is that if we attempt to transform space to time just using Taylor's hypothesis, we can get a good collapse for a long time, a long spatial, which is long time, but not for the short space, which is short time. However, when you use the elliptical model and use your data, you actually can get a full collapse of all the correlations onto a single curve. Furthermore, the black line is actually the spatial correlation, independent, again, as if you'd made uncorrelated measurements. This is a spatial autocorrelation. And you get a collapse between the temporal results being mapped to the spatial domain and the spatial autocorrelation. The 0th order explanation is then that the elliptical model provides an improved relationship between space and time. It's just not Taylor's hypothesis. Okay? And so again, what this implies is that the frozen flow hypothesis is not valid, and it would lead to an underprediction of decorrelation. And where this potentially could be important is that if you have models that are highly dependent on your 2-point correlations, depending on the significance of those correlations, again, you can underpredict the decorrelation. So this also gives physical insight. Well, the one thing we also wanted to do was say, okay, now we've shown that the elliptical model seems to work in reacting flows. How can we use this to understand a little bit about the decorrelation process? Since this is a shorter talk, I'll save a lot of the details, but imagine we now do this at all radial positions. And let me explain this. On the top graph is a comparison between the u parameter we derive from our space-time correlation maps and the published mean axial velocity from the TNF database. On the bottom is the v parameter that comes from our map and the u prime RMS that's measured. Again, we have the red symbols are our u parameter that we derive, and the black are the TNF databases at 2 different axial locations, and similar in the velocity, the v parameter and the u prime RMS. What we show here is that as a function of radial position, let's try not to get too confused by different axial positions, but for a given axial position, the u parameter that comes out, which is supposed to be representing the convective portion of the decorrelation, actually falls upon the axial velocity very well. Okay, so this is expected. The second thing, though, that we have is that the u prime RMS falls on top of the v parameter very well, okay? And so we can now start to get a physical understanding that the decorrelation, okay, the physical reason why we're decorrelating is due to these convective effects and this small scale turbulence, okay? And I know I'm running out of time, but I do want to show one or two slides from a collaboration I had with Wolfgang on auto-ignition dynamics. Why did we want to study this? Well, this nice work by Christoph Arndt and Wolfgang showed that auto-ignition is temporally repeatable but spatially intermittent. And so the goal was to to look at the role of mixing fluctuations. So here's a technique that we did that used two cameras of OH chemoluminescence, one looking directly or pseudo-directly at the flow and one looking down the laser sheet to make sure the kernel formed in the laser sheet. And then we used Rayleigh scattering along with processing, taking advantage of the known relationship between signal and constituents, and then enthalpy conservation. And the bottom line was that we could get a method to derive both the mixture fraction and the temperature field up until the onset of ignition. Okay, and therefore we ended up with a pretty good method. The results from here were that the ignition kernel always formed in the periphery, these very low mixture fraction regions, and this was primarily due to the fact that it's forming essentially in this cusp here where you have very low scalar dissipation. So it needs to be very lean, hot, and have very low strain and scalar dissipation rate. But since everyone's hungry, I will skip stuff on resolution, and one of the things that we want to do, FRS and me scattering, you can come ask me about it. And then, so let me just put my final comments up since everyone's stomach is growling. Okay. Discussion topic, these are my conclusions, okay? Significant capital investment over the last decade. There's a tremendous amount of appeal in high-speed imaging. We have a lot of really cool tools, how best to use them. Some things that come to mind, of course, always are transient physics, harsh environments, and limited data collection window, these high-pressure rigs. But the question is, what are our galloping horse questions? What is it that we should target these measurements? And again, a thought on model assessment. Can we determine new metrics? I don't know. Can we get higher sensitivity, meaning metrics that have higher sensitivity, or are they just an expensive supplement to low-order statistics? That's where I'll quit.
Noel Clements, UT Austin. So I'm just curious what you have your sampling frequency is it 10 kilohertz, and how does that compare to the bachelor frequency?
So that's a wonderful question, and if I had a 45-minute talk, I would give you this slide. So basically, I can't do the math, but basically we can compute for any given flow. The bachelor frequency for the flames that we were looking at when you're at about a radial position or 2 is about 7 kilohertz, okay? But it really depends on, as you know, where you're at. And this is one of the things I wanted to talk about is that the bachelor frequencies, depending on where in the flow, can be hundreds of kilohertz. I mean, they can be these tremendously high quantities where you're not resolving the small scale fluctuations at all. And so the stuff that we've done for the space-time maps are actually where we do resolve the bachelor frequency by at least 1.8. We try to do Nyquist, but sometimes they're about 7. Yeah.
Okay. And I mean, you can actually sort of exceed it or whatever, be lower than it. It depends on what kind of correlations you're looking at, right? Ones are more sensitive to large scales, but you just can't do anything with the smaller scale.
Are you asking, do we try to delineate that data? Or?
Yeah, well, I guess it, so you don't meet the bachelor frequency, I guess, ever. Is that right?
No, we would in the hotter portions, you do meet in the flame, you do meet the bachelor frequency. You do exceed it. We can more than sample.
Right, but you should be double.
Right, yeah, we can go well more than when you get near the flame. In the axial positions, they get actually quite low.
Okay, I'm just saying that, but even if you're not meeting Nyquist,
if you're not meeting them,
you can still do some things.
Yeah,
with
and what we do for space-time map is we'll usually look at, again, 5 kilohertz subsampling and look at the correlations and to make sure they're the same. Mm-hmm. Okay, and it really depends. One of the questions I was going to talk about, it depends on what you're interested in. It really comes down to what length scales you can resolve. If you can only resolve a millimeter, there's no reason to make a 200 kilohertz measurement. You're only watching this thing convect past a much larger scale. There's no reason to make a high fidelity measurement. So I sort of have this map, but I won't talk about this. There should be a close coupling between Reynolds number, your spatial resolution and your temporal resolution. These are all intimately coupled. And then there's always going to be a weakest link there.
And then in the Raman, is the spatial resolution and the temporal resolution?
Yes, they're matched. The spatial is about 300 microns, and it's to match to be the appropriate surrogate to the 10 kilohertz. Okay.
Thanks.
Any other question? Okay, then. Thanks.